welcome back. So, let us recall we have defined the Fourier coefficient for a Riemann integrable function which is 2 pi periodic, and we define f hat of n which is equal to 1 by 2 pi 0 to 2 pi f of x e to the power minus of I n x dx, and we have computed Fourier coefficient of various functions, and the Fourier series is defined to be summation over n varies over z f hat of n e to the power I n x. And we have no a priori knowledge that given any Riemann integrable function this series is going to converge. But what we have seen is that if f belongs to C k, recall that C k is the consist of 2 pi periodic functions which kth derivative exists and kth derivative is continuous. In that case, what we have seen is that f hat of n is less or equal to some constants which may depend on f, but not on n mod n to the power k. So, therefore, for k bigger than 1, we have the Fourier series of these functions, they converge, but till now we do not know whether they converge to f or not. Okay, so, in order to talk about the Fourier series converges or not, so first question what one would like to ask from our previous knowledge of convergence of series, we know that if C n is a sequence of complex number, if this series converges, then mod C n this goes to 0 as mod n goes to infinity. This is a necessary condition for a series to converge. It is not sufficient, all of us we know. So, now that means it makes sense to ask, if C n is f hat of n e to the power I n x, then mod C n is mod f hat of n. Does mod f hat of n converges to 0 as mod n goes to infinity? What we have seen that only easily by triangle inequality that this is less or equal to some constant which is depend on f. Namely, this constant is 1 by 2 pi integral 0 to 2 pi mod of f of x dx. Now, this quantity is going to come again and again. So, it is let us give a symbol to this, let us give it the symbol this, which I will be calling it that norm of f. Okay. To answer this question, we have the Riemann Lebesgue lemma, which states that let f be a 2 pi periodic Riemann integrable function then converges to 0 as mod n goes to infinity. So, at least what we can see from this result, which is a celebrated result, that the necessary condition for the series to converge is there. Okay, so, to write the proof for this, so let us write down f hat of n. This by definition is 1 by 2 pi, then 0 to 2 pi f of x e to the power minus of I n of x dx. Now, this I can write 1 by 2 pi and I multiply a negative sign 0 to 2 pi f of x e to the power minus of I n x into e to the power minus of I pi dx, because e to the power minus of I pi is cos pi, which is negative 1 and negative 1 is here. So, this is minus 1 by 2 pi. Now, this is 0 to 2 pi, this is f of x e to the power minus I n x plus phi by n dx. I will take n not equal to 0, because we are interested for large value of n. So, we can assume this. Now, if I make a change of variable, then this is going to be minus of 1 by 2 pi. This is becomes f of x minus of pi by n, and then this is a minus of I n x dx, and the limit which is going to be whatever it is. If we make a change of variable, that x going to x minus of 1 by n, this is minus of 1 by n to 2 pi minus 1 by n, but nevertheless both the function f and e to the power I n x is 2 pi periodic. So, it does not matter which 2 pi length interval I am integrating. So, this again I will keep it as 2 pi. Now, this is also our f hat of n. Now, if I add these two, then I am going to get 2 f hat of n, which is equal to 1 by 2 pi 0 to 2 pi f of x minus f of x minus of n e to the power minus of I n x dx. Now, for n large, x minus of 1 by n, it converges to x. Now, if f is continuous, then f of x minus 1 by n will converge to f of x. So, now if it is a continuous function, it is uniformly continuous because of the compact interval 0 to 2 pi. Therefore, for f continuous, what we have got is that 2 f hat of n, this converges to 0 as mod n converges to infinity. So, for f continuous function, we have got our Riemann Lebesgue lemma. Now, how to get for arbitrary Riemann integrable function? Recall that we have seen this for f, if we are using r of 0 to 2 pi, this 2 pi periodic Riemann integrable function, then there exists a sequence f k of continuous function such that integral 0 to 2 pi mod of f k of x minus of f x dx, this goes to 0 as k goes to infinity. Now, for fk's, this sequence, they are continuous, each fk is continuous. Therefore, Riemann Lebesgue lemma holds. Now, look at f k hat of n minus of f hat of n. This what we have seen is by triangle inequality is lesser equal to 1 by 2 pi 0 to 2 pi mod of f k of x minus of f of x dx. Now, this goes to 0. This will imply now f hat of n, because f k hat of n, all of them they go to 0. Therefore, f hat of n also goes to 0 as mod n goes to infinity. Therefore, what we have got is the Riemann Lebesgue lemma for Riemann integrable function with this approximation result. Okay, so good. So, now we have at least the necessary condition. So, now we need to see that whether it is true that for every Riemann integrable function the Fourier series converges or not. In order to ask this question, so let us understand what is the meaning of convergence. The convergence of this series means we define the partial sum S n f of x, this is equal to summation over minus of n to n f hat of n e to the power I n x. Now, let us try to look closely how this partial sum looks like. Now, this is equal to summation over minus of n to n 1 by 2 pi 0 to 2 pi f of y e to the power minus of I n y dy e to the power I n x. This is equal to 1 by 2 pi is scalar, we can take it out. Now, this is a finite sum. So, we can interchange the sum and the integral by the linearity of the integral. We can write this 0 to 2 pi f of y d this is summation minus n to n e to the power minus of I n or e to the power I n x minus y, then this is dy. Now, this is a function. So, let me denote d n of x, this is equal to summation minus n to n e to the power I n x. Therefore, this is equal to 1 by 2 pi. Symbolically, I can write this as f of y d n of x minus of y dy. This d n is called Dirichlet kernel. Now, because to make significance of this, let me put nth Dirichlet kernel. So, this suggests, this simple observation suggests us that in order to understand the convergence of the Fourier series, we need to understand the behavior of d n x. Now, let us see what exactly this function dnx or the Dirichlet kernel looks like. So, a simple derivation will say dn of x, this is equal to now if I take e to the power minus of I n x outside, then this becomes the first term is 1 plus e to the power I x, and this goes up to e to the power I 2 n x. Now, this is a geometric progression. So, all of us we know how to add. If we are in a geometric progression, the sum is going to be 1 minus e to the power I, this is 2 n plus 1 of x divided by 1 minus of I x. Now, this is equal to e to the power minus of I n x minus e to the power I n plus 1 x divided by 1 minus e to the power I x. Now, in order to have the symmetry, if I am taking out e to the power I x by 2, then this one is e to the power minus of I n plus 1 half of x minus e to the power I n plus 1 half of x. Now, similarly, from the bottom, if I take e to the power I x by 2, I get e to the power minus of I x by 2 minus e to the power I x by 2. So, this 2 gets cancelled. Now, this is the symmetry. So, this is going to be minus 2 I sin n plus 1 half x divided by minus 2 I sin x by 2. So, therefore, this is sin n plus half x by sin x by 2. So, this is what one form of the Dirichlet kernel will look like, the nth Dirichlet kernel will look like. Now, to see certain properties. So, what happens? So, now limit x goes to 0 sin n plus half x by sin x by 2. Now, this is we know that sin x by x, limit x goes to 0 is 1. By doing that, what we will get is, so this is equal to, if I write it as x goes to 0 sin n plus half of x divided by n plus half x into n plus half x, and then x by 2 divided by sin x by 2, and then 1 over x by 2. So, this term goes to 1, this term goes to 1, x gets cancelled. So, this is n 2 n plus 1 by 2 into 2, which is equal to 2 n plus 1. So, this means d n of 0, this is 2 n plus 1. Now, let us try to draw at least d 1 of x, how this is going to look like. Now, this is at 0, this is going to take the value 3. Now, this is my pi, this is my minus of pi. So, for this, so sin 1 plus this has to be 0 in order to have d 1 x is 0. This will imply that 3 by 2 x is equal to plus or minus pi. This will imply x is equal to plus or minus 2 pi by 3. So, now this is 2 pi by 3 and then this is minus 2 pi by 3 and d 1 of pi is a negative number. So, this is going to be, then if I draw this graph, this is something will look like this. This is our d 1. Now, look at for d 2. So, d 2 at x equal to 0, this is going to take the value of 2 n plus 1, that it means 5. So, let me take this as 5 here d 2. Now, let me find out what are the zeros of d 2 can have. So, now basically here in this case 5 by 2 x, this is equal to sin 5 by 2 x is equal to 0. So, therefore, this is going to be equal to n pi. Now, what are the kind of n? So, now this is x has to be 2 n by 5 pi. Now, x we are considering on minus pi to pi. So, 2 n by 5 pi has to be less than pi and which has to be greater than minus of pi. Therefore, this will tell us that n is equal to 1, 2 and minus 1 minus 2. So, therefore, for n equal to 1, this is 2 by 5, this is 2 by 5, n equal to 2 is 4 pi by . So, similarly, this is minus 2 by 5 pi and then this is minus 4 pi by 5. Now, here this is 0. So, d 2 is going to look like this. So, similarly, if we go for any arbitrary n, then we can find between minus pi to pi, we are going to have 2 n plus 1, 1 to 2 n zeros. So, therefore, for arbitrary n, this is something which is going to look like so, now on this side, so this is going to be something like 2 n plus 1. So, this is going to oscillate like this. Something like this. So, now as we can see, the when we are taking n larger and larger, then the Dirichlet kernel is going to pick up at 0, and in the rest away from the 0, it is going to vanish and oscillates too much, because there will number of zeros will be 2 n in that interval, and this is going to happen that there will be too many times it is going to cross the x axis, and it is going to take more value, large value, if we are considering n to be large. Okay, so, now what we need to see is that we need to get the Sn of f of x minus of f of x. That is our target. We want to show that this modulus is less than epsilon, given an epsilon positive for large n. This has to be small. Now, this is equal to, let us give an attempt and to understand how we are going to attack this problem. This is equal to integral f of x minus of y d n of y dy and minus of f of x. This 2 pi should be inside the modulus. This is what is as per our definition. So, now this is integral. So, we would like to have one integral over here. So, now observe integral 1 by 2 pi minus pi to pi d n of y dy. This is equal to 1 by 2 pi minus pi to pi summation of minus n to n e to the power I n y dy. Again, this is a finite sum. We take this integral, interchange the integral and the sum. So, what we are going to get, this is minus pi to pi e to the power I n y dy. Now, what we know is that this is the fundamental observation for this course is that minus pi to pi e to the power I n x dx. This, as you can see, is that if n, this is equal to 1 if n is equal to 0. Now, if n not equal to 0, then e to the power I n by I n minus pi to pi, and they are going to have the same value. This is a 2 pi periodic function at the end point. So, this is going to be 0. So, this is very important relationship, easy, but the fundamental concept of the Fourier analysis. So, in this case, if we are coming back to the computation of the integral of d n y, then what we get here, this is going to survive only when n is equal to 0. Therefore, this is going to be equal to 1, because for rest of the n not equal to 0, this is going to be 0 except for n equal to 0, and we get that to be 1. Therefore, when we write this S n f of x minus of f of x modulus, I can write this as 1 by 2 pi and then mod of minus pi to pi f of x minus of y d n y, and in the term f I can write 1 by 2 pi minus pi to pi f of x d n y, because 1 by 2 pi integral minus pi to pi d n y is 1. So, this is equal to 1 by 2 pi f of x minus of y minus of f of x, then this is d n y dy. Now, by pushing the modulus inside, what we will be getting, that this is less or equal to mod of this and mod of d n y. Now, let us say that f is a continuous function, then for small y, f of x minus of y minus f x is going to be small. So, now for and then we are left with absolute value of integral of d n of y for small change in if y is small. That is what we will see it in the next lecture, that by breaking this integral into small y near 0 and breaking and away from 0, what we are going to get. Thank you.